In this video, we're going to talk about the maximum likelihood principle. And the idea is, in statistics, if you measure some data, so you have your sample, and you have an idea of what the distribution is, if it's a normal distribution or a Poisson distribution or whatever distribution that would be a good model, these distributions, excuse me, these distributions involve parameters. But of course, you're not going to know what the parameters are from what you've measured. So the question is, how can you predict what the parameter, what the best parameter would be, let's say, for the model? Because different parameters are going to give you different distributions. So you want to have a good idea of what the best parameter would be to get the most accurate prediction. And basically the idea behind maximum likelihood estimates, which is what we'll talk about, is this maximum likelihood principle. So the maximum likelihood principle says that given a data set, you want to choose the parameter or parameters in such a way that the data are most likely. So, for instance, suppose, let's think about how we can turn this into a math problem that you can solve. Suppose that your data set consists of n numbers, x1 through xn, and suppose that you have your distribution that you think can be used to model the data, and let's say it has parameter theta. So we'll let p of theta of x be the probability mass function in case your random variable is discrete, or f sub theta of x, that will be the probability density function in case you have a continuous random variable. So remember that your probability mass function, p sub theta, that by definition is the probability that your random variable, capital X, is equal to little x, right? And then when you have a continuous distribution, the density function is what you integrate to figure out the probability that your variable is between two given numbers. Okay, well, so for your way of measuring the likelihood, so we have a function of the parameter theta that measures the likelihood that you will get the sample x1 through xn if your distribution has that parameter theta. So we define L of theta in the case of a discrete distribution. We define L of theta to be the probability that your first random variable is little x1, that your second random variable is little x2, all the way to xn. So you have n different random variables that we're assuming come from the same discrete distribution, right? Okay. And we're assuming that these are independent. So this will just be the probability that x1 is little x1 times the probability that x2 is little x2, times the probability that capital Xn is little xn. Well, that's just the definition of the probability mass function, right? That's just p sub theta of x1 times p sub theta of x2 to p sub theta of xn. Because we're assuming that all the xi's have the same probability mass function. So that's the definition of L of theta. This is called the likelihood function. So given your x1 to xn, you're going to get different likelihood functions, right? Your likelihood function depends on x1 to x, what the little x1 to xn are, because it's the probability that you get x1 to xn as a function of theta. Okay, so that's pretty simple in the case when you have a discrete distribution. Now notice that when n is 1, then the likelihood function is just the probability mass function. Okay, so now we have the continuous case. Now the continuous case is going to be different because you have a continuous random variable, and the probability that x1 is little x1 is 0, right? So it can't be this. But to define what the likelihood should be, let's give some idea of what it could be. So suppose that epsilon is some small number. Okay, so this is more about the intuition, right? So the idea is we want to choose theta so that the probability, so we, instead of, that capital X1 is x1, let's just think about when your x1 random variable is between little x1 minus epsilon and little x1 plus epsilon. And we have that for all of the xi's. So capital X2 should be between little x2 minus epsilon and little x2 plus epsilon, all the way to little xn minus epsilon is less than or equal to capital Xn, which is less than or equal to little xn plus epsilon. So instead of thinking about what's the probability that the xi's are equal to little xi, which would be 0, we just have some small epsilon, and we think about what's the probability that capital X1 is within epsilon of little x1. Well, by the independence, this is just going to be the probability that capital X1 is between little x1 minus epsilon and little x1 plus epsilon times the probability that capital X2 is between little x2 minus epsilon and little x2 plus epsilon, all the way to the probability that the capital Xn is between little xn minus epsilon and little xn plus epsilon. Well, each of these probabilities is what's the integral of the probability density function, right? So it's the integral of f sub theta from x1 minus epsilon to x1 plus epsilon times ... to the integral of f sub theta of x from xn minus epsilon to xn plus epsilon. And the idea is that when epsilon is really small, right, each of these integrals is approximately, this is just approximately f sub theta of x1. Well, times 2 epsilon. Times 2 epsilon. Of course, it's not just that. It's that times 2 epsilon, right? Because you are integrating some function from x1 minus epsilon to x1 plus epsilon, and your function is approximately 1 epsilon is really small, so here's x1 in the middle. You have f of x1, and if you think about the area under the curve as basically sort of like a rectangle with height f of x1, and then the base is 2 epsilon, right? Then the area of this rectangle is just f of x1 times 2 epsilon. And the area of that rectangle is approximately the area of under the curve. And we're basically using the midpoint approximation of the integral. Okay, so it's approximately that, and then that's for, x1, and then you do the same thing for xn, so f sub theta of xn times 2 epsilon. So this would be 2 epsilon raised to the nth power times f sub theta of x1 dot 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 f sub theta of xn. Okay? And the idea is that this is a fixed epsilon, and so if you can make this as big as possible, so we choose theta to maximize this, right? Epsilon is fixed, so if you want to maximize this, you want to vary your theta, you want to choose your theta that maximizes this this probability. Oops, I didn't write a complete sentence. So that this is maximized. This being this probability. Well, we want to choose theta so that f sub theta of x1 times dot 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 times f sub theta of xn is maximized. And that leads us to define, so we define the likelihood function to be the product of the density functions. Evaluated at x1 through xn. So notice that this is very similar to what we had for a discrete case where we multiplied the probability mass functions together. That made sense because that's actually the probability of getting x1 to xn, right? But in this case, we gave some heuristic, motivation for why we would multiply the probability density functions in the case of a continuous distribution. And again, notice that when n is equal to 1, you just get the probability density function. Okay, so that's your L of theta in the continuous case. Here's an example in the continuous case. Let's say, let's just take n equal to 1. Okay. And suppose that you measure something that is given by an exponential distribution. So you have f sub lambda of x is lambda e to the minus lambda x. And you have something that you believe is distributed in terms of an exponential distribution, and you get a sample of, so you get the data set, which is x1. So you take one sample and you get x1, right? And the question is, what is the lambda that maximizes the probability that you ended up getting x1? Well, that would be, okay. That would be L of theta equals F sub theta. Well, in this case, it's lambda, right? Your theta is equal to lambda. So L of lambda equals F sub lambda of x1, which is equal to lambda e to the minus lambda x1. Now notice the x1 is a fixed constant, and you're trying to find the lambda that maximizes this. So we have to use some calculus, right? So one way to do it is to take the derivative of both sides with respect to lambda and set it equal to 0. So to find lambda that maximizes L of theta, one thing you can do is you can calculate L prime of lambda and solve L prime of lambda equals 0. Because you're trying to figure out when this is a maximum. You know from calculus that this happens. Well, in this case, we don't have endpoints. Right? I mean, I guess the endpoint would be, one endpoint would be lambda equals, well, it's not even lambda equals 0, but that wouldn't even work. So there are no endpoints to this. And so your maximum is going to occur at a critical point, right? When the derivative is 0. All right, so let's take the derivative. So L prime of lambda, we have to use the product rule, because remember we have our variable showing up here and here in the product. So it's going to be first times the derivative of the second, so it's going to be, okay, minus x1 e to the minus lambda x1, right? And then plus e to the minus lambda x1. So you set this equal to 0. Now you factor out the e to the minus lambda x1. So this is equal to e to the minus lambda x1 times negative lambda x1 plus 1, right? This is equal to 0. You can multiply both sides by e to the minus lambda x1 because that is never 0. And so you get that negative lambda x1 plus 1 equals 0. And that implies you just add lambda x1 to both sides and then divide by x1, you get lambda equals 1 over x1. Now, if you think about it, that's not very surprising that you get 1 over lambda x1, because we know that the mean of an exponential distribution is 1 over lambda. Right? So like your x1 would be 1 over lambda. So yeah. And that makes sense because the mean of the exponential distribution is 1 over lambda. Okay. Another way of doing it, which is often more typical, well, it's easier usually in the case when you have a product of a bunch of things, and here you have a product, right? The likelihood function is a product, is to maximize the log of the product. Because we know that log is an increasing function, so hopefully you learned in calculus, well, if you have a function and then you are trying to find the maximum of it, and then you apply an increasing function to it, so you take like the log of it or you take the square root of that function, that composition of functions is maximized at the same place as where the original function is maximized. Right? The x that maximizes the original function is the same as the x that maximizes the square root of that function, or the logarithm of that function. So we could also just maximize the logarithm of the likelihood function. Well, in this case, L of lambda is lambda e to the minus lambda x. So if you take the logarithm of it, And logarithm means the natural log. Of course, any log will work because you have an increasing function. But since we have e, we might as well use the natural log. So you're going to get the natural log of lambda plus the natural log of e to the minus lambda x, right? Because the natural log of a product is the sum of the natural log. So you get ln of lambda, and then that is going to be minus lambda x. Okay, well, this is x1. Okay, now we need to take the derivative of this. So we take the derivative with respect to lambda, and we are going to get 1 over lambda minus x1. And we set this equal to 0, and we solve for lambda, and again, as we expect, we get x1 equals 1 over lambda. So that's what happens in the case of an exponential distribution. Where your data set consists of only one point. Okay. What happens in general when you have your data set consisting of x1 through xn? And again, this is with the exponential distribution, right? So we're trying to find the lambda that maximizes the probability that you end up getting this data set x1 through xn. Okay. Well, this is just the what we did before was the case of n equals 1, and now we're doing it in general. So L of lambda is going to be lambda e to the minus lambda x1 times all the way to lambda e to the minus lambda xn. And this we can write as lambda to the n times e to the minus lambda times x1 plus dot 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 all the way to xn. So we could do either approach. First one is to just take the derivative directly using the product rule, or we can take the log of it first. And I think I'm going to take the log of it first, the natural log. And what I'm going to get is I'm going to get the natural log of lambda to the n plus the natural log of this exponential term. And this ln of lambda to n is equal to n times natural log of lambda, right? And then the other term is just going to be minus lambda times the sum from x1 to xn. So now we take the derivative of this with respect to lambda, and that's going to give us n over lambda minus the sum from x1 to xn. And we set that equal to 0, and when you solve for lambda, you are going to get lambda equals n over x1 plus dot 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 plus xn. And that's equal to 1 divided by the mean of the xn's. Okay? So this lambda, that's what we call the maximum likelihood estimate. So for instance, if you suspect that something is described in terms of an exponential distribution with the parameter lambda, and let's say that you take one measurement and you get 2, okay, and you had to guess what lambda was, you would guess that lambda is a half from the maximum likelihood approach. If you took 2 measurements and you got 2 and 5, well, the sum of 2 and 5 is 7, and so the mean is 3.5, right? 7 over 2, and so your guess of lambda would be 2/7. So that's the maximum likelihood estimate.